Language functions, the brain, and sex differences. Language functions are distributed in many areas of the brain, but the regions shown in Figure 9.6 are especially significant. Broca's area, located to the left hemisphere's frontal lobe, is most centrally involved in word production. Wernicke's area, in the rear portion of the temporal lobe, is more centrally involved in speech comprehension. People with damage in one or both areas typically suffer from aphasia, an impairment in speech comprehension and/or production that can be permanent or temporary. The visual area of the cortex is also involved in processing written words. Years ago, scientists noted that men who suffer left hemisphere strokes are more likely than women to show severe aphasic symptoms. In female stroke victims with left hemisphere damage, language functions are more likely to be spared, suggesting that more of their language function is shared with the right hemisphere. Brain imaging research supports this hypothesis. In their study, men and women engaged in a language task in which words and non-words were presented on each side of a computer screen. Participants had to identify which was the real word as quickly as possible by pressing one of two computer keys. Functional MRIs were recorded during the task and during a non-language control task. Men exhibited greater left hemisphere activation during the language task, whereas women's brain activation occurred in both the left and right hemispheres. Maximum activation occurred in regions corresponding to Broca's area and Wernicke's area. Neural systems involved in several aspects of language may be organised differently in women than in men. But because this finding has been successfully replicated in some studies but not others, more research is needed to sort out why these inconsistencies occur. Further, as a critical thinker, you should recognise that if men's and women's brains differ overall in some aspects of language processing, this finding does not establish by itself whether those sources of those differences lie in our genes or possible gender differences in language socialisation. Acquiring a first language. Language acquisition is one of the most striking events in human cognitive development. It represents the joint influences of biology and environment, nature and nurture. Many language experts believe that humans are born linguists, inheriting a biological readiness to recognise and eventually produce the sounds and structure of whatever language they are exposed to. Biological foundations. Linguist Noam Chomsky proposed that from birth, our genetic endowment innately leads us to interpret part of the environment as linguistic experience. He has argued that we are born with a brain mechanism already pre-wired to understand general grammatical rules common to all languages, which he terms universal grammar, such as the principle that languages contain elements that are arranged in particular ways. Chomsky's views have generated much debate, including disagreements about whether we are born with brain systems specifically dedicated to language, or instead have more general inborn cognitive capabilities, example memory and learning, that by themselves can account for language acquisition. Several facts suggest a biological basis for language acquisition. First, human children, despite their limited thinking skills, begin to master language early in life without any formal instruction. For example, whether born in Sydney, Samoa or Siberia, young infants can perceive the entire range of phonemes found in world's languages. Between 6 and 12 months of age, however, they begin to discriminate only those sounds that are specific to their native tongue. For example, Japanese children lose the ability to distinguish between the R and L sounds because their language does not make this phonetic distinction. But children exposed to English continue to discriminate these sounds as they mature. Likewise, Japanese-speaking children learn the syntactic rule to put object before verb. Ichiro the ball hit. Whereas English-speaking children learn the syntactic rule that the verb comes before the object. Ichiro hit the ball. Moreover, despite their differences at the phoneme level, all adult languages throughout the world, including sign languages for the deaf, which developed independently in different parts of the world, seem to have common underlying structural characteristics. Language acquisition appears to represent the unfolding of a biologically primed process within a social learning environment. Social learning processes. Given the required biological foundation, social learning plays a central role in acquiring a language. Early on, caregivers attract children's attention and maintain their interest by conversing with them in what has been termed child-directed speech, a high-pitched intonation that seems to be used all over the world. Caregivers also teach their children words by naming objects, reading aloud, and responding to the never-ending question, "What dat?" The behaviourist B.F. Skinner developed an operant conditioning explanation for language acquisition. His basic premise was that children's language development is strongly governed by adults' positive reinforcement of appropriate language and non-reinforcement or correction of inappropriate verbalizations. Most modern psycholinguists doubt that operant learning principles alone can account for language development. For one thing, children learn so much so quickly. By year 2 in primary school, children have acquired about 5,000 to 6,000 words. Observational studies also show that parents do not typically correct their children's grammar as language skills are developing. Rather, parents' corrections focus primarily on the truth value or deep structure, which was the interpretational meaning of a sentence, of what the child is trying to communicate. They are less likely, for example, to correct a young child who says, "I have 2 foots," than they are to correct one who says, "I have 4 feet," even though the latter statement is grammatically correct. Further, much of children's language is different from that of their parents, and thus it can't be explained simply as an imitative process. Nonetheless, social learning is a crucial contributor to language acquisition, and language development reflects an interplay of biological and environmental and social factors. Developmental timetable. Language acquisition proceeds according to a developmental timetable that is common to all cultures. As Table 9.1 shows, children progress from reflexive crying at birth through stages of cooing, babbling, and one-word utterances. By 2 years of age, children are uttering sentences called telegraphic speech that at first consists of a noun and a verb, want cookie, with non-essential words left out. Soon, additional words may be added, daddy go car. From that point on, speech development accelerates as vocabulary increases and sentences become more grammatically correct. In the short span of 5 years, an initially non-verbal creature has come to understand and produce a complex language. Many linguists believe there is also a critical period, or at least a sensitive period, from infancy to puberty during which the brain is optimally responsive to language input from the environment. If exposure to language is delayed beyond this period, then normal language acquisition either will not occur, the critical period hypothesis, or will still be possible but much more difficult to achieve, the sensitive period hypothesis. Some support for at least a sensitive period for language acquisition comes from studies of children who lived alone in the wild, feral children, or severely neglected children who were isolated from human contact by neglectful parents. These neglected children may have been kept locked in a room with virtually no contact with other people. When extreme neglect begins early in infancy and continues through the years in which children normally start using language, the children typically have little or no speech or understanding. Language-deprived children who were found when they were past puberty acquired only limited language skills despite extensive training. Attributing the cause of language delay in these children is difficult. They may have been abandoned or neglected because of developmental delay or childhood psychosis, both of which would have impeded language development. Even in potentially normal children, inferring that their speech delay is entirely due to isolation would be inappropriate, because they have usually also suffered untreated illnesses and malnutrition severe enough to impair brain development, as well as language deprivation. So children found past the sensitive period or the first 5 years in age usually don't develop much language, but that could be because of an untreated illness or malnutrition, which has impaired brain development, or because they may have been developmentally delayed as little children in the first place. So at 1 to 3 months, infants can distinguish speech from non-speech sounds and prefers speech sounds, phonemes. Undifferentiated crying gives way to cooing when happy. Then at 4 to 6 months, babbling sounds begin to occur. Child vocalises in response to verbalisation of others. At 7 to 11 months, perception of phonemes narrows to include only the phonemes heard in the language spoken by others in the environment. Child moves tongue with vocalisation. Child discriminates between some words without understanding their meaning and begins to imitate word sounds heard from others. And 12 months, first recognisable words typically spoken as one-word utterances to name familiar people and objects. For example, da or block. 12 to 18 months, child increases knowledge of word meanings and begins to use single words to express whole phrases or requests. For example, out, to express a desire to get out of the crib, primarily uses nouns. 18 to 24 months, vocabulary expands to between 50 and 100 words. First rudimentary sentences appear, usually consisting of two words, example, more milk, with little or no use of articles, the, conjunctions, and, or auxiliary verbs, can and will. This condensed or telegraphic speech is characteristic of first sentences throughout the world. 2 to 4 years of age, vocabulary expands rapidly at the rate of several hundred words every 6 months. Two-word sentences give way to longer sentences that, though often grammatically incorrect, exhibit basic language syntax. Child begins to express concepts with words and to use language to describe imaginary objects and ideas. Sentences become more correct syntactically. And again, syntax is the rules that govern the order of words, so the way that we say them. So, bananas have sale for I violates the syntax. 4 to 5 years, child has learned the basic grammatical rules for combining nouns, adjectives, articles, conjunctions, and verbs into meaningful sentences. The importance of early language exposure applies to any language, not just spoken language. Because sign languages share the deep structure characteristics of spoken languages, deaf children who learn sign language before puberty develop normal linguistic and cognitive abilities without having ever heard a spoken word. In contrast, deaf people who are not exposed to sign language before age 12 show language learning deficits later in life, which seems to lean towards that sensitive period that you need to learn language by. Bilingualism. For those of us trying to learn a second language, there are inspirational models. M.D. Berlitz, inventor of a well-known system for teaching foreign languages, spoke 58 of them. Sir John Bowring, a former British governor of Hong Kong who reputedly could speak 100 languages and read 100 more, noted that it is scarcely more difficult to acquire 5 languages than it is to acquire 1. These people are termed hyperpolyglots, defined as fluency in 11 more languages, in recognition of their outstanding linguistic ability. Bilingualism, the regular use of 2 languages, is common throughout the world. In New Zealand, 3 official languages can be used in legal proceedings: English, Maori, and New Zealand Sign Language. English is spoken by 95.9% of people, Maori by 4.1%, and New Zealand Sign Language by less than 1%. More than 6,000 New Zealanders can communicate in all 3 languages. English is the sole official language in Australia, but as in New Zealand and other countries, a history of immigration means that many languages and bilingual combinations are spoken. Many Europeans speak 2 or more languages, and 3 is not unusual, although native English speakers are less likely to learn another language really well. Does bilingualism affect other cognitive abilities and first language learning? In childhood, does learning a second language influence the development of other cognitive abilities or affect acquisition of one's native language? Causation is difficult to establish because researchers typically don't get to randomly assign children to bilingual or monolingual classrooms. Nevertheless, research suggests that bilingualism is associated with greater thinking flexibility, higher performance on non-verbal intelligence tests, and better performance on perceptual tasks that require people to inhibit attention to irrelevant information and pay attention to relevant information. One psychologist suggests that people who learn a second language gain continuous experience in using selective attention to focus on relevant information and ignore information that interferes with a task. For example, while speaking in their second language, bilinguals must ignore the more familiar words of their first language. Bilingual children also gain experience in frequently switching languages, which may contribute to their greater cognitive flexibility than monolingual children. Bilingualism, however, may also have a linguistic cost. When children are raised learning two languages, they develop a somewhat smaller vocabulary in each language than do their monolingual age peers. And this vocabulary size difference is also found among bilingual adults. At present, research suggests that in general, compared to monolinguals, bilinguals tend to perform more poorly on several linguistic tasks, but display superior performance on other types of cognitive tasks. The bilingual brain. 2 language systems or one? Is a second language represented in the same parts of the brain as the native language? One intriguing set of findings come from studies of bilingual people who experience a brain trauma, example from a tumour or a stroke, and subsequently develop an aphasia. In some bilingual patients, the same linguistic ability, such as understanding the meaning of words, may be impaired to different degrees in each language or impaired in one language and not the other. Moreover, when brain damage patients produce similar impairments in both languages, patients may experience some simultaneous recovery in both languages or recovery in one language but not the other. These findings suggest that there is variability in how bilingual abilities are represented in the brain, and also that, in some cases, each language is represented by at least partially distinct neural networks. The question, are there 2 language systems or one, is far more complicated than it looks. The answer may depend on the aspect of language examined, example, word recognition, grammar, the age and proficiency of second language learning, the degree of exposure, similarity of the 2 languages, and other factors. Still, brain imaging studies shed some interesting light on this issue. The most consistent finding is that when people acquire a second language early in life, both languages use a common neural network. In contrast, people who learn a second language only moderately well later in life, such as in adolescence or adulthood, typically show more variability in their neural activation patterns. At least for some language functions, their specific brain areas that process each language are partly distinct. Further, even for some cortical areas involved in processing both languages among older bilingual learners, greater activation tends to occur when the person uses the second language. This suggests that the person may have to exert more conscious effort to process the less dominant second language. Age and second language fluency. Many people start to learn a second language during high school or university, or after emigrating to a foreign country during late adolescence or adulthood. Can these late learners achieve the fluency of native speakers? The answer is often tied to the hypothesis that there is a biologically based critical period for acquiring a second language, typically processed to end by late childhood to the mid-teen years, after which the capacity for true native-like acquisition is essentially lost. In a nutshell, some psycholinguists believe that evidence supports a critical period hypothesis. Others don't and still believe that there are critical periods for acquiring some aspects of a second language, for example, speaking without a foreign accent, but not other aspects, example, learning grammar. One finding is clear. Overall, people who start learning a second language in late adolescence or adulthood achieve less proficiency than younger learners. Importantly, this occurs even when the various age groups have similar amounts of exposure to the second language. How can we reconcile these and similar findings with those of other studies that generally report that about 5 to 20% of adult second language learners achieve native-like proficiency on various language tasks? Recent research illustrates how answers to questions such as, can adult second language learners achieve native-like proficiency, depend strongly on how native-like proficiency is defined and measured. First, they identified 195 native Spanish speakers who began learning Swedish at various ages and who considered themselves to have native-like Swedish proficiency. Next, native Swedish speakers acted as judges and listened to speech samples from these participants and from a control group of native Swedish speakers. Based solely on the speech samples, 10 judges classified each participant as being a non-native or native Swedish speaker. Lastly, the researchers administered a battery of Swedish language tests to native Swedish speakers and to a sample of bilingual participants classified by a majority of judges as being native Swedish speakers. This is like a tongue twister. The judges correctly identified all the native Swedish speakers. Although all the bilingual participants believed they spoke Swedish with native-like fluency, the judges thought otherwise, especially among the adolescents and adult participants. Further, only 7% of bilingual participants demonstrated native-like proficiency on the entire battery of 10 language tests, and these all came from childhood learner groups. Based on the results, scientists argue that to attain native-like second language proficiency, acquisition must start in childhood, and even that may not be sufficient. Other psycholinguists argue that criteria for judging native-like proficiency can be too stringent, and thus the debate continues. Reading. Typically, as long as we are exposed to an environment rich in spoken language, we will learn to produce and understand speech. Reading is a different animal. It requires extensive instruction to become a fluent reader. If written language came to humans as naturally as spoken language, there would not be almost 759 million non-literate adults across the globe. Learning to read. Reading has been called one of the most cognitive complex tasks that we will ever learn to do. In the English language, for example, we must first learn to visually recognise a set of basic symbols, 26 letters, that constitute the alphabet, as well as other visual elements such as punctuation marks and number symbols. We also learn names for these symbols, our ABCs. One of the most intricate steps in learning to read and write an alphabetic language such as English is making connections between how letters and letter combinations look when written and how they sound when spoken. For example, note how the letter A is voiced differently in each of the following 5 words: mat, marble, mall, and mean. Likewise, E is voiced differently in met, meet, and ache, as are various letter combinations such as CH in channel versus ache, ACHE. If you are fluent in reading English, these phonological variations pose no problem. When learning to read, however, they frustrate attempts to apply simple rules such as the letter A always sounds like A and the letter E always sounds like E. This ability to translate print into sound, to have a mental map that connects written symbols to phonemes, is itself dependent on more basic understandings about the properties of language. As children acquire speech, they not only learn how to manipulate phonemes to produce different words, but also become aware that words are constructed from sequences of sounds and thus that words can be decoded into more basic sound elements. Psycholinguists use the term phonological awareness to refer to this overall awareness of the sound structure of one's language, and it is an important predictor of young children's subsequent reading ability. Recognising written words. Fluent reading involves rapid word recognition. Previously, we discussed a claim that, and this is all done with the first and last letter in the right order, and we see these things on Facebook all the time where they're all jumbled up but the first and letter are the same, and it says, it doesn't matter what order the letters in a word are, the only important thing is that the first and last letters are at the right place. This is because we do not read every letter by itself but the word as a whole. Anonymous, 2003. So the letter ordering claim was false. Words with interior jumbled letters can be very difficult to read. So what's the validity of the claim that we don't read individual letters but instead read words as a whole? One way we might recognise words as a whole is from their overall shape. The basic idea of the century-old word shape hypothesis is that words have a holistic form or envelope based on their pattern of letters. Several types of evidence have been offered to support this hypothesis, including the interesting finding that mixing lowercase and uppercase letters, which disrupts a word's typical shape, slows down word recognition. And I'd have to agree, because it took me just a smidgen of a millisecond longer to read the word interesting, which they had put in every second letter as a capital. I hate it when people type like that as well. Anyway, but mixed casing has other negative effects, such as making it more difficult to perceive some lowercase letters. And these, rather than overall shape disruption, appear to cause the reading impairment. Overall, there is substantial evidence against this simple word shape envelope hypothesis. Although visual information contained near the boundaries of letters, in the upper and lower points of letters, for example, like a B and a P or a Q or a G, or a T, have the upper portions and the lower portions of the letters, may contribute more to word recognition than visual information in the middle portion. How then do fluent readers recognise written words? The issue isn't settled, but several lines of evidence point to at least one key component: the parallel processing of letter information within words. At a basic visual level, the brain simultaneously analyses the features of multiple letters, acquiring information about individual letters and letter groupings, and coding their location. Some psycholinguists propose that our brain directly processes this visual information to determine the meaning of a word, while others contend that our brain also phonologically recodes printed text to help determine word meaning. But in any event, the notion that fluent reading does not involve visual processing at the level of individual letters appears to be wrong. Our brain is also processing other information as we read. Without conscious awareness, as in listening to speech, prior written words create top-down context effects that help prepare us for recognising the words we're about to read. Additionally, our eye movements while reading are not smooth and continuous. We alternate between briefly fixating on a word, typically for a quarter second or less, and then making a rapid, distinct jump, called a saccade, to another word. And some of these saccades are backwards, example right to left when reading English. During fixations, our brain is receiving information from our visual periphery about the spacing of upcoming words, which helps determine how large our next eye movement will be. So reading is a complex process. It depends on many brain areas, including ones specialised for detecting and recognising visual features of objects, coding the identity of letters and their positions within words, processing the phonological aspects of language, and encoding the meaning of words. For fluent readers, all this machinery exists under the radar screen. It seems effortless. Unfortunately, many children and adults struggle with reading, and this includes people diagnosed with dyslexia, which is a specific learning disability that affects people's ability to read, write, and spell. Can other animals acquire human language? Non-human species communicate in diverse ways. Chimpanzees grunt, bark, scream, and make gestures to other chimps. Dolphins make clicking sounds and high-pitched vocalizations. Many species use special calls to warn of predators and to attract mates. In some species, communication shows interesting parallels to human language. Just as humans have different languages, each songbird species has its own songs, and just as humans have a sensitive period in childhood for language acquisition, some songbirds will not sing normally in adulthood unless they hear the songs of their species while growing up. Although other species communicate, the capacity to use full-fledged language has long been regarded as the sole province of humans. Some scientists have attempted to challenge this assumption by teaching other species, such as apes and grey parrots, to use human language. I'm not sure how to pronounce this, but this is WASHOE, so washu, early signs of success. So at first, investigators tried to teach chimpanzees to speak verbally, but chimps lack a vocal system that permits human-like speech. A breakthrough came in 1966 when Alan and Beatrice Gardner took advantage of chimps' hand and finger dexterity and began teaching sign language to a 10-month-old chimp named Washu. They cross-fostered Washoe, raising her at home and treating her like a human child. By age 5, Washoe had learned 160 signs. More important, at times she combined signs, example, more fruit, you tickle Washoe, in novel ways. Other researchers also had success. For example, a gorilla named Coco learned more than 600 signs. Then we have Project NIM, Dissent from Within. Behaviourist Herbert Terrace taught sign language to a chimp he named Nim Chimsky. Oh, like Noam Chomsky. That's very cute. A play on the name of linguist Noam Chomsky. But after years of work and videotape analysis of Nim's conversations, Terrace concluded that when Nim combined symbols into longer sequences, he was either imitating his trainer's previous signs or running on with his hands until he got what he wanted. Moreover, Nim spontaneously signed only when he wanted something, which is not how humans use language. Terrace concluded that Nim had not learned language. Some ape language researchers disputed Terrace's conclusions. They agreed that although Washoe and other cross-fostered apes signed mainly to request things, other types of communication also occurred. Roger and Deborah Fouts continued working with Washoe and other cross-fostered chimps. They refrained from signing in front of Luli, Washoe's adopted son, and found that Luli acquired over 50 signs by observing other chimps communicate. The chimps also signed with each other when humans weren't present, and signing occurred across various contexts, such as when they were playing and fighting. Then we have Kanzi, Chimp versus Child. Sue Savage Rumbaugh has worked extensively with a chimpanzee species called the bonobo. At age 1.5, a bonobo named Kanzi spontaneously showed an interest in using plastic geometric symbols, that were associated with words. By age 4, with only informal training during social interactions, Kanzi had learned more than 80 symbols and produced a number of 2- and 3-word communications. Kanzi typically combined gestures and symbols that he pointed to on a laminated board or typed on a specially designed keyboard. For example, Kanzi created the combinations person chase Kanzi, Kanzi chase person, and person chase person to designate who should chase whom during play. Kanzi also responded to spoken English commands. Sounds very similar to a dog, except chimps have opposable thumbs. They also tested Kanzi's ability to understand unfamiliar spoken sentences under controlled conditions. For example, when told, "Give the doggy a shot," Kanzi picked up a toy dog, grabbed a toy hypodermic needle, and gave the dog a shot. For comparison, one of the researchers' daughters, Alia, was tested under the same conditions between the ages of 2 and 2.5. Kanzi correctly responded to 74% of the novel requests and Alia to 65%. In short, Kanzi was comprehending speech at the level of a human toddler. But is it language? Recall that human language is symbolic and structured, conveys meaning, is generative and permits displacement. Apes are capable of communicating with a small vocabulary of symbols and hand signs. They can convey meaning by using 1 or 2 symbol communications, example banana or give banana, and have also produced some longer symbol strings that convey meaning. As for structure, there are examples of how apes follow and violate rules of grammar, but overall the evidence for ape grammar has been disappointing. Lastly, the evidence for generativity and displacement is limited and controversial. Critics, even those impressed by Kanzi's feats, are not persuaded that apes are displaying language. Some believe that ambiguous ape communications are interpreted as language because the researchers erroneously assume what must be going on inside the apes' minds. Conversely, proponents believe the data show that apes can acquire rudimentary language skills, a so-called proto-language that lacks major qualities of true human language. If nothing else, this intriguing scientific work should remind us to appreciate something that we often take for granted, namely, the seemingly natural ease with which humans acquire full-blown language. Language, culture, and thinking. Does the language we speak shape how we think? The linguist Benjamin Lee Whorf took an extreme position in this matter, contending in his linguistic relativity hypothesis that language not only influences but also determines what we are capable of thinking. If the linguistic relativity hypothesis is correct, then people whose cultures have only a few words for colours should have greater difficulty in perceiving the spectrum of colours than do people whose languages have many colour words. To test this, Eleanor Rausch studied the Dani of New Guinea, who only have 2 colour words in their language. Wow, one for bright, warm colours and the other for dark, cool ones. She found that contrary to what strict linguistic determinism would suggest, the Dani could discriminate among and remember a wide assortment of hues in much the same manner as can speakers of the English language, which contains many colour names. Similarly, in the Amazon, the language of the Munduruku people contains few words for geometric or spatial concepts. Yet Munduruku children perform as well on many geometric and spatial tasks as Western children. Other research, however, comparing English children and Himba children from Namibia, suggests that colour categories in a given language have a greater influence on colour perception than Roche's study of the Dani suggests. The English language contains 11 basic colour terms, whereas the Himba language has only 5. Himba children made fewer distinctions among coloured tiles than did English children. For example, Himba children categorised under the colour term Zuzu a variety of dark colours, such as dark shades of blue, green, brown, purple, red, and the colour black. English children distinguished amongst these colours and remembered the different hues better when retested on ones which they had seen earlier. Still, most psycholinguists do not agree with Wolff's strong assertion that language determines how we think. They would say instead that language can influence how we think, categorise information, make decisions, and perceive our experiences. Consider, for example, the ability of sexist language to evoke gender stereotypes. In one study, university students read one of the following statements. The statement is, "The psychologist believes in the dignity and worth of the individual human being. He is committed to increasing man's understanding of himself and others." Psychologists believe in the dignity and worth of the individual human being. They are committed to increasing people's understanding of themselves and others. The students were then asked to rate the attractiveness of a career in psychology for men and women. Those who had read the first statement rated psychology as a less attractive profession for women than did the students who read the second statement, written in gender-neutral language. Apparently the first statement implied that the psychology is a male profession, when actually the majority of psychology PhDs awarded over the past decade went to women. In such ways, language can help create and maintain stereotypes.